I'm going to speak today on building fault-tolerant applications. Some of that, we're going to spend a little time really starting off and talking through faults. What are all the different kinds of ways you can break your stuff? I have run into every different kind of physical failure. I've had buildings that have caught on fire for the infrastructure that we were running for systems. I've definitely had a dump truck back up into the power wire and disconnect power. We had a friend of mine that was building his system up that accidentally poured a cup of coffee into the router. Every different kind of physical failure that's possible, and a whole bunch above that. The networking that you've deployed, the code that you've deployed. Does Bill come on time? The classic example is Fred got hit by the bus. Every one of the different layers of your stack, from the facilities that you run in, all the way down to the people that run your infrastructure, every one of those things is a possible driver of fault. And we're going to talk today about fault tolerance. How do we build infrastructure that's designed to survive fault? And we're not talking about an absolute thing here. This is not a binary, I am fault tolerant and now my application won't fail, and I'm not fault tolerant and I could fail anytime. What we're talking about is degrees of risk mitigation. Each one of those different possible causes of fault has a given likelihood. That likelihood is associated with a cost on the other side of mitigation. Some mitigations are really easy to implement. You add an extra semicolon someplace, or you ensure that you've clicked a button on our infrastructure. Those kinds of changes are the ones we want to walk you through so that you're doing the easy things you can do, the inexpensive things that you can do to increase fault tolerance. And then beyond that, as you identify places where there's real risk for your business, real risk for your applications, for your customers' data, we'll make it so that if it's worth value to your business, that there's a way to build applications that are fault tolerant there too. We also really strongly believe that fault tolerance is not typically something that can be done with your fingers. If someone has to run over someplace and poke something that's semi-fault tolerant or human-based fault tolerance, we like automation. We like systems that are doing this on their own. We like systems that are programmed to react faster than most of us can. And we like it when you've tested this stuff. So we'll go through some examples for that. The agenda for today, I'm going to talk a little bit about the Amazon Web Services approach to fault-tolerant application design. We'll talk about how that's a little different and how cloud has changed the way that companies build and deploy these kinds of systems. We'll talk about our building blocks. What has Amazon built that you can use to get to fault-tolerant? And then I'll have Bulat from Twilio will come up and show how they've, in specific, built a very, very successful fault-tolerant application for their phone and text messaging system that's really, really a powerful application on us. And then we'll go through a couple of quick final design patterns. I think it'll make a lot of sense and make it a lot easier for you to build in a way that fits the best practice. So if you used to do this, sort of old school fault tolerance, why build one when you can build two twice the price? Right? It's really the easy way to get around almost all of the bad choices you could possibly make. Buy the really expensive one and then buy two of them. That way, if one breaks, there's not an issue. We don't think that that works, and we think that cloud has proven that there are approaches that make more sense. And there are really sort of the standard obvious places where that is, but you've been talked through for a lot of, I think, the last couple of tracks about what are the sort of obvious cloud computing benefits. These benefits translate to fault tolerance. So we'll make it so that there isn't an upfront capital expense for a highly available architecture. We'll make it so that your backups don't cost so much to run. We'll make it so that your disaster recovery is really only something you pay the big bucks for when you need it. We'll make it so that delivering fault-tolerant applications is easier, is faster. You can get that stuff to market more quickly. One way that we've been trying to help people understand about it is that the AWS Cloud allows you to overcast a little bit. You get this shadow infrastructure that's there. We've built a pile of machines. We have a pile of infrastructure ready for you to use, but you don't have to pay for that capacity until you need it. So you get this little sort of extra shadow bit that's ready, just like you'd have to normally pay for that stuff up front, but you only pay for it with us when you're using it. We know that there are really significant barriers to the difference between a disaster recovery approach, where someone is calling you and yelling at you about things being broken and you think there's a pretty clear way that you can fix it, and the new approach, which is highly available, where no one's called and there's no pagers and things are just working even though there's been some kind of a physical or a structural device that's failed. We know that there are big cost and complexity and expertise challenges to this. You've really got to be able to not only learn how to use all of these new parts, but do so in a scalable way. So to sort of step into the Amazon parts for this. We've really built in two different strategies. You heard talks from a couple of different folks. Werner even mentioned it during his keynote. The systems that we deploy as services, DynamoDB, S3, SimpleDB, each of the simple integration services, SNS, SQS, SES, Simple Workflow, all of these pieces are delivered as services by us to you. And that choice, that design, includes, by default, Amazon's work on fault tolerance. So if you need a queue system that is fault tolerant, we built one of those, we'll sell it to you a little tiny piece at a time. That might be the easiest and quickest way to get to a fault tolerant application that's there. There are some applications here that we haven't already built and sell to you as a service. Probably the number one candidate there being the application that you built. We didn't build that for you, sorry. That's something that you'd have to go work on. We have built components, application components like EC2, like EBS, like RDS databases, where with the right configurations, with the right deployment, the right implementation, you're able to get to a fault-tolerant architecture that can be as resilient, as redundant as the services we built, or forget it, you can make them more redundant. We have S3 today in a regional area. I have no problem if you want to make a copy of your data in every AZ, in every region across the globe. You've made a lot more copies than we've made when we put it in S3. You win, you get to put more nines down than we did. So that stack of infrastructure, the componentry that's either a service from Amazon or a component that you can use to build your own services, is the sort of split in our infrastructure. And we'll spend most of the time talking about how to build fault tolerance on the ones that you have to make the choices on the right-hand side list. So we know that there are opportunities for failure at every one of the layers in the stack. From there's a geographical disruption, there's an earthquake, there's a flood, there's a tsunami, there are problems, up through problems with individual facilities, the networking, the configuration of your systems, the management of those configurations, the deployment of that management and configuration, the actual resources themselves. We've built fault-tolerant pieces at each of the layers of the stack. So we have regions that are available around the globe. We have availability zones. We have Route 53 for DNS and elastic IPs for addresses. We built Cloudformation for programmatic management of deployments. We built Cloudwatch alarms and auto-scaling to allow you to manage the deployments of individual pieces of the infrastructure. And then each of the building blocks, the Amazon Machine Images and EC2 instances, those systems are all designed to be used in a coordinated fashion to build an all-together fault-tolerant stack. So let's drill into each of those pieces. We have 8 regions available today. Those regions are distributed intentionally around the globe. They're not all right next to each other. They're there so that you can build those kinds of fault-tolerant environments. They also help with latency. They also help with compliance if you have issues with sort of specific country laws. But we think that the original intent, the original goal there certainly is to get to those sort of broader and larger environments. As you move down the stack into the availability zones, I think you've seen these kinds of topologies a bunch of different times. The real goal is to take the layers of your application and make them redundant across availability zones. Part of the one optimization to do there is to minimize the crosstalk between those zones. We have a charge associated, costs you a penny a gig if you want to move data zone to zone. And part of that is not because it's a gigantic expense on our side. Part of it is to encourage those kinds of isolated environments where you're loosely coupled, where the left side of the stack isn't talking so often to the right side of the stack, so that they really do fail independently. So if a whole AZ were to go, the left side would keep running and everything would keep moving. We've also built tools that allow you to span those distant groups. So the elastic load balancer allows you to distribute traffic across the AZs. Another building block that makes it very straightforward, very tangible, very easy. That's all programmatic. It's all scriptable. When you use an auto-scaling group across AZs, the load balancers will handle that. So it makes it pretty approachable to do this level of work. We also know a big driver of complexity in all of this is network. So we built fault-tolerant network design tools. What's the difference between a 107 address and one of the 50 addresses in our fleet? The 50 addresses are typically EIPs. And EIPs can move around from instance to instance. That's loosely coupled, and as a result, that's fault-tolerant. You can take an instance that's failed, move its IP address from one machine to another machine. That is the simplest, poor man's way to move traffic from one to the other. That's the beginning sort of ingredient of fault tolerance. We already talked a little bit about elastic load balancing, and one of the questions that we've heard a lot, like, isn't then the ELB a single point of failure in my infrastructure? Really critical thing to point out. ELB itself is a service from Amazon, just like the other services that I described. So I'm here to assure you that there is not a single point of failure in the physical topology of the ELB device. It is designed to survive the same kinds of failures that your infrastructure, being built of multiple instances, is designed to survive. We've also built automated DNS. We know a huge number of the most sophisticated systems for redirecting traffic between nodes, ensuring that the names are consistent as machines start and stop. Those kinds of design elements are much easier when you don't have to go all the way back to the weird shared hosting provider where you bought your DNS in the first place and remember that funky password and type in, this is what the CNAME is supposed to be. Bring that stuff over into the same API context so that it's very, very easy, so that it's programmatic, so that it can be deployed by the same control tools you already use, so that it can be managed in the same context and deliver the same kinds of benefits from a fault-tolerant standpoint. We've also just added a feature to that, a hugely important feature from fault-tolerant standpoint in latency-based routing. So now you can have one DNS entry from us that points to all the different regions that you have access to, all the different regions that you have active systems in. And the folks that come in to use your resources, we figure out which region they're closest to and route the traffic to the appropriate place. That used to be something you had to get outside of Amazon. We've added that in as a feature. That's not just to make things faster. It also makes it so that if one of the regions isn't working today, the other regions can handle the load. So now you're not stuck. You're not in this position where DNS becomes a single point of failure. We fixed that too. Another huge layer as you sort of move that one step up the stack is the application deployment, application management. I think the big question, the thing to sort of noodle as you're looking through your application is, when you deploy the application stack that you have, is that unique? Is that totally new in yours? Do you manage individual servers in a way that no one else does? If it's unique, we have a system called Cloudformation where we'll package up your stack, we'll help you deploy it more rapidly. AMIs are a part of that, but Cloudformation lets you build complex topologies that have multiple nodes. Maybe you need the first part of your app tier, and then you need another section of the app tier as another instance. Or maybe you need mid-tier load balancing with HA proxy, or you need other kinds of software tools in there. Cloudformation lets you create an actual atomically deliverable individual stack out of your stuff, as opposed to, I have to build this part, and then the next part, and then the next part. Builds that into a process. If, on the other hand, your stack is not unique, if you use Java just like everybody else, if you have PHP code just like everybody else does, and you just need it to go, we have a thing for that too. It works the same way, called Beanstalk. It's maybe an easier way to understand what Beanstalk does. It's really just a Cloudformation script. It's really just a way to programmatically deploy your stack. So we know that you're going to have a stack of some kind, whether that's in these languages or not. If it's not in these languages, you end up using Cloudformation or some of our great partners, EngineYard, Heroku, some of the other guys that have built great stuff there. You can build your own stack too. I don't have any issue with that. We have a lot of folks that have made that choice. But it's a place where you need to make the investment in understanding those tools and ensure that you have some expertise there so that when you're designing the way that that's deployed, you're designing it in a fault-tolerant way. We've also built a lot of signals in our system. So it's not just what the API reads back. Now you have Cloudwatch that is able to tell you, how much CPU am I using or how much network is going on. You can custom put metrics into Cloudwatch. So if you have application monitoring software like Nagios or Ganglia, or there's a pile of those different tools, you can write from them into Cloudwatch. So now you have another access point for automated actions. Maybe that's not even autoscaling. Autoscaling is a great tool. But maybe you're using Cloudwatch metrics to trigger other kinds of actions, construction of new simple queues or construction of new backup objects in S3. There are a bunch of patterns for allowing these systems to interact with each other based on those kinds of automatic triggers, automatic signals that come out of our environment that make it a lot easier to build those more distributed, more fault-tolerant workflows. We also know a lot of folks have built a lot of Amazon machine images. I don't know if you've seen the catalog recently. I read through it. I think there's over 10,000 AMIs at this point.
Really important that any AMI you use is with either something that you've built or with somebody that you have a relationship with. We want you to be able to identify the constructor of that. It's an important piece of building a fault-tolerant application. But we also know that there isn't anything built into the AMI system that allows automatic, programmatic management of their contents. They are a fixed golden image. The whole point of having an ID on those things is so that you aren't changing them. You want to maintain their consistency. But their maintenance is critical. Software gets updated all the time. So whether you use programmatic deployers like Chef, like Puppet, like some of the third-party management tools like RightScale or others, if you use those sorts of systems, they'll build the image that you're going to use on your behalf. If you're not using something like that, you need to do this maintenance. You need to ensure that you're rebundling and repatching based on your newest versions of your code and the newest versions of the application software that you're using. That builds fault tolerance in from a security standpoint, from an update standpoint. We also really suggest at this point, we've made a recent change, the M1 smalls, the C1 medium instances, very popular for small parts of the application, which used to only run 32-bit, now allow 64. So you can use the same AMI from 1 core and 1.7 gigs all the way up to 8 cores and 68 gigs of memory. Huge span of vertical scalability on the same AMI. So really important, you also recognize that the regions themselves are logically isolated. So if you're going to use AMIs as the building block of your infrastructure, really critical that you replicate those across regions. If we had some kind of catastrophic event in Singapore and all of the AMIs there were lost, you'd want to have a copy of your image in another region. That's a process where you'd create it, hydrate it as an EBS volume, replicate those bits to the other region, and resave as a new image. That takes a little bit of work at this point. It's a task. It's something that we've heard from customers that there's a feature request there. There are a few more things we need to build for sure. But this is a place where today there are plenty of patterns for getting those Amazon machine images back and forth across the regions. We also built, we think, the sort of single simplest thing, which is virtualized machines that allow you to build and deploy on demand. I think the sort of normal building block pieces, yes, they're consistent and reliable. A large will always run the same speed and size as another large. You can do reserved instances to increase the likelihood to make sure that you have access to instance hours when you need them. You can use EBS volumes for advanced persistence on your disk. But probably the sneakiest, the most important difference between this and any other environment you've worked in is just absolutely immense fleet scale. This system is gigantic. When you grow like Pinterest did, when you grow like these other businesses, you need to be sure that the fault isn't that you're too big. So having enough machines around so that when it's time to rebundle and redeploy, when it's time to update your software and you're going to start a whole other fleet of machines, having enough of them is its own kind of fault tolerance. We've also recently added a pretty important feature, elastic network interfaces. So in our VPC environment, you can now have 2 distinct interfaces with their own IP addresses hooked to the same instance. That allows you to not only have internal network, not external public network, but internal network addresses for different channels of communication. But those addresses are just like elastic IPs in that they're movable from instance to instance. So now you're talking about remapping the middle tier and the app tier, database tier components from node to node. We have a lot of companies that come to us, maybe you're built this way. This is a typical, absolutely straightforward, N-tier, forklifted application. You take what you have in your colo and you remake it with us. You treat us like we're a web hoster, not like we're a cloud. And as a result, you build this thing. It's in one AZ. It's probably got a master-slave database, but they're in the same building. You've got software load balancers all over the place that you pay full instance hours for. You probably just have the 2 machines that are as big as you need to ensure that if one fails, this if you go to a colo, this is highly available. This is high-end design. That is not the way to do it. We drag people, kicking and screaming sometimes, through to do the work to do fault-tolerant design. You're using auto-scaling at the front tier and hopefully at the app tier. You got software load balancers to ensure that that's a loose coupling. You got elastic load balancers out front and Route 53 DNS between. You're using RDS, or you're managing replication across availability zones on your own for database tier. You're using a cache service. You can use Memcached on your own. You can use our elastic cache. I don't care which one, but put a layer between your databases in the front end. That's just a good idea. I do this presentation a lot I walked through, and this next slide is actually built by one of our customers. I walked through this whole thing, said, this is the way you're supposed to build it. If you're going to go build an app, man, build it this way. And he said, that's a lot of work. Why can't I just build it like this? Any of the stuff that wiggles, put it over in the Beanstalk. Any of the stuff that's not supposed to wiggle, put it over in the S3. All the dynamic code goes over here. All the not dynamic code goes over here. I'm done. Tap it out. Like, that's accurate. If your application fits in a stack manager and your application has static assets, there are huge numbers of programs that have big, hairy stuff just like this, very, very complicated topologies, paying for instance hours, paying for configuration time, paying for IT guys to straighten all this stuff out when they need that. That pushes so much work off onto us. It's such a simpler design. It's 2 boxes. So it's your pick. Like, I like both ways. I have customers that have gigantic fleets that are this way, and there are plenty of applications that are great reasons for this kind of design. At least do this. Please don't do that. Please. Please get here. And we have really great assets. There's lots and lots of documentation that makes it pretty easy. We have a bunch of videos that try to make clear all the different sort of steps that you go through. And if that stuff seems heavy, it might be a good indication to you that this is a good way to go, right? If 30 pages of docs on how to set up the API calls for running through and doing auto-scaling is too heavy, it might be a sign to you that a stack is a way to save effort, a way to save energy and time, and a way to get to market more quickly. So I'm going to take a break for a second and have Bulat from Twilio come up. Twilio has taken this to heart. They've built a very, very scalable, very, very highly available application.
Thank you, Miles. Hi, everyone. So like Miles said, my name is Bulat, and my last name is long. I'm very happy to be here today to share with you how we think about continuous delivery under high availability constraints. So I'm going to start by asking how many of you have actually heard or know of Twilio? Please raise your hand. That's quite a lot of hands. Thank you. But for those of you who don't know what Twilio is, and this is giving me a little bit of a hard time. OK, so Twilio is actually lets developers add voice and SMS communications to their apps and lets their apps interact with telecom network that's been a black box for all this time before Twilio. And we basically sit between carriers and developers, and we abstract all the carrier communications away and give developers one simple API that they can use to initiate a phone call or send a text message and do all sorts of workflows around that. The Twilio Toolbox consists of the 3 tools primarily. The REST API itself, which developers can use to initiate a phone call, for example, or send a text message. Then we have the Twilio markup language, or TWIML, which developers use to tell our server what to do when certain events occur, when a phone call comes in, for example, or when a short message comes in, or at any other part of the life cycle of the communication. And a little less than a year ago, we released Twilio Client, which is a JavaScript library and a set of mobile SDKs, iOS and soon Android, for adding voice and presence communication capabilities to your mobile applications, be them in the browser or on mobile. And you could assume you can do quite a lot of stuff with that kind of tool set. And we've seen customers or Twilio customers implement things from contact centers and interactive voice response applications to business process automation, marketing campaigns, call tracking, lead generation, click-to-call, social networking, all of that stuff that you couldn't previously do. And some of our customers include big names like Walmart or eBay or Sprint. Sprint, huh? So we're a phone company. And since we're a phone company, we can't go down because no one likes dropped calls, right? Plus, our international SMS and voice offering guarantees that at all times, somewhere, someone will be there making a call or sending a message. So we have to be available 24/7 globally. And the way we think about that kind of availability is by following a set of engineering principles that I'm here to share with you today that Twilio has been following from its inception and that allowed us to achieve the kind of fault tolerance and high availability that we're capable of today. So let me start with containing failures. We think about failure in units, and the smallest unit of failure is a single host. So we build our systems so that they're able to recover when any host in the cluster goes down, for example, or any 2, 3 hosts, however many. And we also think about availability zones and regions as units of failures as well, so our system is built to handle those failures too. And to give you an example of that kind of isolation, you could have a web server that writes to a database, and you could write to a database directly, but then in case that remote database goes down, your web server goes down as well. So you see that domino effect of one failure causing failures all over the system and making it unpredictable. So you could use a local queue on the web server machine itself to enqueue the writes and actually dump them to the database asynchronously. And that will give you some time to recover in case the remote database goes down, and that time is very valuable. Alternatively, when you perform reads, we use load balancers on the box, the local load balancer on every box, that load balances reads between a pool of slaves. So in case one of the slaves go down, we're able to rebalance the queries to the slaves that are actually up, and that will give us time to recover the slave that went down as well. Another important principle is ability to fail fast. By failing fast, I mean raising exceptions as soon as they occur, do not suppress errors, and this involves a certain way of writing code that is sprinkled with assertions and exceptions that, for example, might look like this, and if you're writing C. And the reason failing fast is important is because if you fail fast, it gives you the ability to retry on failure. And when you build a fault-tolerant system, you expect failures, and you have to be able to retry in case they happen. And the sooner you fail, the sooner you're able to retry. But don't forget to include timeouts so that your system doesn't lag down in case of some long network communication happens and you actually fail fast. Another important principle is being idempotent. Idempotent is a very weird word, right? So let me try to give you an example. Let's say you were building a bank account application in a fault-tolerant manner. You could build it without idempotence in mind, but if you had built an application that was idempotent, that means that no matter how many attempts you do to deposit money to an account, you actually deposit the money only once, because otherwise it would be a very bad bank, right? Another important principle is being stateless, and the reason is that data persistence is actually one of the hardest problems scalable software as a service companies face nowadays. Because it's very hard. You have to manage backups, you have to do replication, you have to do all sorts of crazy stuff. And so at Twilio, we constantly try to look at our stack and evaluate where we can get rid of statefulness and use a stateless architecture instead. Another way to do it is by offloading your databases to some third-party vendor like Amazon with their amazing DynamoDB or relational database services. So you don't have to worry about, you let them worry about. But a common way of making a stateful architecture stateless is in web servers. You might have a pool of web servers that store session information in some common session store. And that is a stateful architecture and poorly scalable. Alternatively, you could just encrypt the whole session data in the cookie and exchange that instead. So that way we just get rid of another database and made our system more stateless. Another important thing is relaxing consistency. Well, you know, CAP theorem says that any kind of distributed computing system cannot achieve partition tolerance, consistency, and availability all three at the same time. So consistency and partition tolerance are very important, because partition tolerance lets you recover from failure without corrupting your data, and consistency is also very important because you don't want inconsistent data. Well, actually, consistency is important, yes, but you can relax consistency, and that way you can actually perform a lot more reads, for example, by doing replication and scale system better instead of going to the same data source all the time, like in this example. Okay, so those are the 6 engineering principles that we try to follow to make systems fault tolerant. But there is also important thing like having a single button test and deploy system, because we don't want engineers to struggle with long deploys. So we try to automate as much as possible of our deployment process as well. But we don't deploy on the same frequency everything. So here is a logarithmic scale of how frequently we deploy different parts of our system. So for example, for every single schema change, we might do 10 API deployments, which includes PHP and Python code modifications, for example. And for every 10 of those, we might do actually 100 website front-end code changes, because they are a lot lower risk than the API changes. And for 100 of those, we might do 1,000 content changes on the website itself, because that's very low risk. But to automate deployments and to be able to build to bring up the full Twilio stack with just one click of a button, we built an internal tool that's called BoxConfig that lets us manage host configuration, orchestration, monitor running hosts, and really eases our lives, because we can build a full Twilio stack with just one single click of a button. And we use monitoring for, we use Nagios for monitoring and alerting of the running host. We use local HA proxy instances for load balancing, like I gave the database example. And this ultimately lets us do multi-center deployments and analytics with a single click of a button. Those are screenshots from the BoxConfig tool itself, where you can see the host list, and here you can see the host details, for example, that gives you links to important Nagios statistics and load balancing stats and various other metrics like CPU, load on the host, and et cetera, et cetera. So Twilio's recipe to high availability and fault tolerance in the cloud is engineering principles plus automation. I know that might not be the panacea, and that might not work for everyone, but that has been our approach, and I was happy here to share it today. Thank you.
Thanks, Balat. Thanks a bunch, Balat. I think that was awesome. So, parts. You know, there's a. I went to a great presentation where someone was building their own physical infrastructure, and the only content of the presentation was just scrolling through the invoices of the stuff that he'd bought, all of the different parts of the gear that he needed to buy. It's a long list. So here's your parts list. Here's the stuff that's in your toolbox. We talked through most of these different components. So at the addressing layer, Route 53 and EIP, at the distribution layer, using multi-AZ design, ELB, CloudFront out front for the edge cache. I'll talk just for a second on CloudFront. Such a gigantic way of insulating yourself from probably the most popular kind of fault, which is death by success. Somebody decides that your front page is the coolest looking thing in the world, and they post to it on Pinterest and all the other interesting websites. All of a sudden, there's this gigantic amount of traffic. If those pictures are in CloudFront, I am telling you, CloudFront will scale, and maybe your website might not. So it's critical. If you have any of that kind of static content, get it off your boxes. It is the least efficient use of this precious compute resource. The largest single driver of your cost in any infrastructure is the compute hours. So really important, if you can get static things out of the way of those machines, you can help unload them, reduce your cost, and increase your fault tolerance. Also important, we think, I watched a great presentation a little earlier today on big data analytics and analysis. We think you should measure everything. There's so much great signal coming out of these systems. Cloudwatch is one of those measures. It's pretty sophisticated for EC2. I think we have more folks writing custom metrics there than anywhere else. But I really encourage you to go take a look at the measures you get back from RDS, or the measures you get back from EBS volumes, or the measures that you get back from these other pieces. Really rich analytics, because those are richer programs. They have more stuff built up, so you'll get all sorts of useful data out of those. Very important piece of the pie. Another important thing around the data tier, which I think everybody spends the most time,
working through and working on how do I get to a place where the data tier systems are fault tolerant. You will be doing these kinds of tasks. You will do patching. You will be caching something. You are going to shard. You're going to distribute. All of that work, it's a lot of work. It takes a bunch of time. You have to be really good at it to be better at it than a lot of other folks. This stuff, I've built a couple of different startups. We spent weeks and months fussing our way through exactly these parts. It takes a huge amount of skill and talent. And frankly, I wasn't that good. It'd be much easier to just work on the sort of shiny website part and the shiny app code part and get back to the job. So Amazon's heard that. We feel that. We've built in the context of that. Amazon.com knows exactly how much work that stuff is. That's why we've invested like crazy at the data tier, to make sure that you've got tools that make this easier, that make this more approachable. In personal experience, DynamoDB is amazing. It does amazing things in this context. It lifts a lot of intelligence, not only from the design of Dynamo, the original of these databases as a paper and real application inside of Amazon.com, but also from the design of S3 and its ability to replicate and build a system that can scale and grow and survive and be highly durable and be highly available. We also know that it's going to take time for folks to refactor their code, to refactor their applications to take advantage of these newer data systems, and that MySQL works real good, Oracle works real good. Real relational databases add a lot of value to a lot of workloads. So RDS helps a huge amount there. Really, really reduces the barrier to entry. I watch folks struggle with the configuration of these systems, with tuning and parameterizing their deployments, with sort of getting the right patch versions together. This is a much simpler way forward. And Elasticache and SimpleDB, these products, they fit the same mold. They're designed in the same way. To dig in a little on RDS, we get some folks that have been confused. MySQL has its own approach for replication. It uses asynchronous replication node to node. Asynchronous replication, as just exactly per the term, has its own risks associated. It's possible you wouldn't have a piece of data over there at the moment that you need it. So we built the RDS MySQL deployment to support synchronous writes between availability zones. You push that button, and we guarantee on the write that is in 2 different places. That's a critical uplift to the performance and enterprise scale and power of MySQL in our context. We also let you use asynchronous replication. We're okay with that. We think it's great for read replicas, though. So we've built that as a push-button deployment as well. Makes it much easier. Probably the easiest and biggest thing that you'd be doing, this is really more disaster recovery, but even doing that right can be chuff, can be a cause of failures. I have customers that have incorrectly set the way that they transmit T-logs off of the system. If you set that up wrong, you're reading too often, you're affecting the performance of the database, that can be a cause of fault. So we've built automation that we've tested and proven and we know works to suck the T-logs off of these boxes every 5 minutes to S3. I'm here to promise. They aren't going anywhere when they're in S3. So if you lose an RDS instance, it's easy to bring those T-logs back into context, to replay the logs, get right back to where you were, no more than 5 minutes of data gone. That's a huge, huge, huge benefit to that system. One of the things we've heard from a lot of folks is, great, awesome. There's a bunch of building blocks from Amazon. I like all that. My application's here. It's on-premise. I don't know how to get it up there. I don't know how to get into context of these data systems. We just added Storage Gateway. That's a great first step. You create volumes in Storage Gateway. They are EBS snapshots. So it's just like you have EBS disks that sit back at your on-premise. You copy your data in there. They are in S3. You can rehydrate them as EBS volumes, and you're ready to go. You bring that data over into the context of your application, and you start to get to work. That works both ways. If you want to bring that stuff back down on-premise, you can drag it that way. We have other features. There's VM import and other tools that are helping folks bridge the gap, make it easier. I think you've heard pretty recently we made an announcement that we've licensed Eucalyptus. So they officially now support and hold our API. That's a part of our growing commitment to making it easier to move things in and out, to making it easier to be fault tolerant in both contexts, to be able to move applications to the place where they're most efficient. I've said the word test a bunch of times. I know everybody likes the monkey slide. You have to show the monkey slide. It's kind of important. Chaos Monkey will be open source. The Simian Army component from our friends at Netflix is really powerful code. There's no reason that you need code to do this. Most of us have enough bad practices in place that you can just trust little intern Tom to accidentally poke the wrong button, and all of a sudden you have a chaos monkey loose in your midst. We think it is the prudent and conservative and professional thing to be testing your applications this way, to ensure that if you pull the plug on pieces, that's instances. But we have folks that have built really complicated versions of this where they'll run every one of the API requests through an API proxy, which runs them back out to EC2, which gives them an opportunity to screw with their own API requests, which means they'll do really nasty things like not attach EBS volumes when they ask to, or switch the network address from one side to the other, or specify a different AMI than you asked for. That's brutal. That makes super, super, super hard to detect changes in your systems. But it means more fault-tolerant applications out the other side. So we think the cool kids do this a lot. It's definitely sort of a nerdy way to spend your time. You don't have to do all of this development all on your own. Hopefully there'll be more and more of that gets open sourced over time. I'm excited about this kind of work because I know that it makes it so that businesses, from the tiny, tiny little startups to the big enterprises that are used to throwing money at these problems, able to build in a way that they can bring things online. There are a bunch of solution architects here. You can sort of tell us apart. We're the geekier looking ones. Happy to answer any of your questions at all after the session about fault tolerance. I really appreciate you taking the time with Balat and I. Thanks a bunch.